Right, hi guys. So today we are going to do some problem solving involving circle theorems. So I'm not going to go through each circle theorem individually, but we're going to do a mixture of problems that will include a number of circle theorems. So this is really about problem solving. But here's a quick recap of our circle theorems. Now, the first two over here, so the angle at the circumference in a semicircle is 90 degrees, is an extension of this second circle theorem here. So the angle at the center is twice the angle at the circumference. And that kind of makes sense because if we think about this angle at the center, this is 180, and this is twice the angle at the circumference, which is going to be 90 degrees. So these two are essentially the same circle theorem, but obviously, if it comes up in an exam, do refer to it as the angle at the circumference in a semicircle is 90 degrees. Here we have angles in the same segment from a common chord. So when we talk about a common chord, so from this point and this point, we can draw a line. This is our chord. And then we can create angles from this chord. So if I use a different color pen, from this chord, I'm creating this angle at the circumference, which is 48 degrees. From that same chord, I can create another angle at the circumference, which is this one over here. And therefore, these two angles, since they are in the same segment at the circumference, they are going to be equal from a common chord. This bit is key. And then we have opposite angles in a cyclic quadrilateral add up to 180. Now, with a cyclic quadrilateral, all the corners need to be on the circumference. If they are not on the circumference, then we do not have a cyclic quadrilateral. So you need to bear that in mind. Okay. And then we have these three over here. So a radius meets a tangent at 90 degrees. This is very important and very useful. And a tangent from the same point, or tangents from the same point, are of equal length. So from this point, I have this tangent here, and then I have this tangent here. These two will be of the same length. A line from the center of a chord bisects the chord at 90 degrees. So from the center, this is our chord, this is our line. That's going to create a 90-degree angle there. And then lastly, we have the alternate segment theorem, which we can see as, let's say, if we have a chord and a tangent, and the angle created between that chord and the tangent is going to be equal to the angle in the alternate or other segment. So this is our minor segment. This is our major segment. Now, from this chord, we are creating this angle over here. So this angle and this angle are going to be the same. And sometimes if you're finding it difficult to see where the angle is, you can create this region here and you'll be able to see that the angle opposite that shaded region is going to be the one formed here. That's 62 degrees. Or, as I said, from your chord, the angle formed at the circumference in the other segment is going to be equal to the angle that's formed between the chord and the tangent. All right, so let's see what this looks like in practice. So here's our first question. Now, it's very important to give our reasons if the question requires us to do so. So we have this question, and what do we know? So we know that this line AB and BD, or AB and AD are both tangents. They are coming from the same point, so they are of equal length. Likewise, we have a radius here and a radius here. So the line DO and BO are also going to be the same length. Now, that may or may not help us, but it's good to label the lines. We know this angle is 50 degrees. It says work out the size of angle BCD. So the angle we are looking for, BCD, is this one over here. So ideally, we need to know this angle here, the angle at the center, because then we can use the circle theorem where the angle at the center is twice the angle at the circumference. Now, the other circle theorem that we could use here is the radius meets the tangent at 90 degrees. And likewise over here, the radius meets the tangent at 90 degrees. So I'm going to say angle ADO is equal to angle ABO, all of which are equal to 90 degrees. And then you need to state your reasonings because it says give a reason for each stage in your working. So the radius meets the tangent at 90 degrees. That's going to be my reasoning. And then I can go ahead and work out this angle here. So the angle at the center. So DOB, so angle DOB is going to be equal to, well, if we think about it, we've got a quadrilateral here, a four-sided shape, and angles in a four-sided shape add up to 360 degrees. So we are going to do 360 minus 90 plus 90 plus 50, and that is going to give us 360 minus 90 minus 90 and minus 50 is going to give us 130 degrees. And our reasoning is going to be angles in a quadrilateral add up to 360 degrees. And this is what our reasoning will be. And then lastly, we can work out the angle we're looking for. So angle BCD is equal to 130 divided by 2, which is going to be 65. And our reasoning is going to be the angle at the center is twice the angle at circumference. All right, awesome. Let's have a go at this one. So again, if you want to give this a go yourself, you can pause the video and do so. So what we have here is an isosceles triangle because we know this length and this length are the same. So we can go ahead and work out these two angles over here. So again, I'm going to say angle BAD, angle BAD is equal to, so BAD is equal to BDA. And they are going to be equal to 180 minus 40 divided by 2. So that's going to be 140 divided by 2, which is 70 degrees. So these angles are 70 degrees. And our reasoning is angles in a triangle add up to 180. And also because this triangle here is an isosceles triangle. Now, what is our next step then? Well, we can go ahead and work out angle BCD. And that is going to be equal to 110 degrees. Now, the reason being is because opposite angles in a cyclic quadrilateral add up to 180 degrees. So this is a cyclic quadrilateral over here, a four-sided shape where all four corners are on the circumference of the circle. So here we are going to say opposite angles in a cyclic quadrilateral add up to 180. So 70 and 110 make 180. And then we can go ahead and work out these two angles over here. And again, our reasoning is going to be because triangle BCD is an isosceles triangle. So once again, we can work out, or we can say angle CBD is equal to angle CDB, which is going to be equal to 180 minus 110 divided by 2. So that is going to give us 35 degrees. So this angle is 35 degrees, and this angle is 35 degrees. And our reasoning is BCD is an isosceles triangle. Okay, so lastly, we need to work out angle ADE. So this is our angle over here. And what we have is a straight line. And we're told this CDE is a straight line. CDE is a straight line. So then we can do 180 minus 35 and 70. So minus 35 plus 70. That is going to give us the total here is 105. So we are going to get 75 degrees over here. And that is our final answer. And our reasoning is because angles on a straight line add up to 180 degrees. So key circle theorem to use here is opposite angles in a cyclic quadrilateral. Okay, let's move on. Now here it says work out the size of angle DOA. So we don't actually need to give our reasonings here. It's good practice to give your reasonings in general, but for the sake of time, we don't need to give our reasonings. We just need to show our workings here. So we know that BOD is a diameter. So BOD is a diameter. Okay. So O is the center. With center O. So this is a radius, this is a radius, and this is also a radius as well. So this line, and this line, they are all radii. And then we have a tangent and a tangent here from the same point, from point C. So this line and this line are going to be of the same length, and they both share OC. So actually what we have are two congruent triangles. These two triangles are identical because all the sides are the same length. So this side here is common in both triangles. Now, we also know that a radius meets a tangent at 90 degrees. So this is 90 and this is 90. So we can work out this angle over here. And we can say angles angle BOC is equal to 180 minus 34 plus 90. So what is that going to give us? And that is going to give us 56 degrees. So this is 56 degrees, which means this angle is also going to be 56 degrees as well, since these two are congruent or identical. And likewise, this angle is going to be 34 degrees. Now we need to work out the size of angle DOA. So DOA, therefore angle DOA is going to be equal to 180 minus 56 plus 56. So that is going to be equal to 68 degrees. And that would be our answer. And the reasoning here would be angles on a straight line add up to 180 degrees. All right, let's have a go at the next one over here. So now it says give reasons for each stages of your workings. So we need to work out angle X over here. Now, what I'm going to do with this question is to draw, and that's a little bit wonky, but I've drawn a radius here, which means I've created an isosceles triangle because this line here is a radius and any line from the center to the circumference is also a radius. So we know that this angle is going to be 29 degrees. So we can say angle OCA is equal to angle OAC. And they are both going to be 29 degrees. And that's because we have an isosceles triangle. So AOC is an isosceles triangle, which then means we can work out, we can work out this angle over here, and that is going to be 90 degrees. And that's because a radius meets a tangent at a right angle. So we can say angle sorry about that. So if we OAT, so angle OAT is equal to 90 degrees because a radius meets a tangent at 90 degrees. Okay, so essentially we've almost completed this problem because what we have now is this triangle over here. which in effect is something like this. So we know this is 29. This whole angle is going to be 119 because 29 plus 90 is 119. And this is going to be x. So in order to find x, we are going to do angles in a triangle. So 180 minus 119 plus 29. And that is going to give us 180 minus those two is going to give us 32 degrees. So x is equal to 32 degrees, and that's because angles in a triangle add up to 180 degrees. Now, there are other ways of doing this question. However, I think this is probably the easiest way. But you could have worked out this angle over here. Excuse me, jump the gun there. You could have worked out this angle over here, and then you could use angles on a straight line to find this angle here. And then since you know this is 90, you've got another triangle, and you can then go ahead and find x. So sometimes there are multiple ways of doing a problem involving circle theorems. Okay, let's have a look at this one. So again, it says work out the size of angle MST. So we don't need to give our reasons, but we can talk about the reasons in this problem. So we know that this is 48. Now, this is the center, and the line is therefore a radius. So a line from the center to the circumference is a radius. And I can again draw another radius. It's a good habit to draw radii where necessary. So we know this angle is going to be 48 because these two are of the same length. And therefore, we can work out angle POS, which is going to be angles in a triangle. So 180 minus 48 minus 48 is going to give us 84 degrees. And then from there, we can work out the angle at the circumference because the angle at the center is twice the angle at the circumference. So this angle here is going to be 42 degrees. And how does that help us? Well, now that I know this is 42 degrees, I can work out this whole angle over here. And I can also work out this whole angle over here because these two are of the same length. And I should draw two lines here so we don't think that this line and this line are of the same length. So we can work out the full angle over here and over here. So in order to do that, I can say MSP, angle MSP is equal to angle MPS. And that is going to be 180 minus 42, so minus this angle over here, and then we need to divide that by 2 since this is an isosceles triangle. So I'm dealing with this triangle over here at the moment. And I'm trying to work out the whole angle, not just parts of it, working out the whole angle over here. So that is going to be 180 minus 42 divided by 2 is going to be 69 degrees. Now, this whole angle is 69 degrees, which brings us to an interesting circle theorem, and that's going to be the alternate segment theorem. Because if you think about it, we have a chord over here, and we are going to have this angle over there. So how does that help us? Well, we're trying to work out angle MST. Well, I know this whole angle is 69 degrees. And if you think about it, the angle formed from the chord with the tangent is going to be the same as the angle formed in the other segment or in the alternate segment. So from this chord, I've created an angle at the circumference in this segment here. So if this whole angle is 69, this one will also be 69 degrees as well. And that makes sense because if you think about this line here, this is a radius. and a radius meets a tangent at 90 degrees. And if we think about this angle over here, in fact, I'm going to shade it in yellow. Well, if the whole angle is 69, 69 minus 48 is going to be 21. And then if I do 21 plus 69, that gives me 80, 90 degrees. So it all makes sense because even my radius meets my tangent at a total of 90 degrees. But really, with this question, you would preferably use the alternate segment theorem. So once you know this angle over here, you can then go ahead and work out the angle over there, which is 69 degrees in total. All right, so we use two circle theorems here. We use angle at the center is twice the angle at the circumference, and then we had to use the alternate segment theorem, where this angle is equal to angle MST. Okay, so what is our final answer? Our final answer is going to be angle MST is equal to 69 degrees. Okay, brilliant. So let's move on to another question. Now here it says prove that the tangent ABC is parallel to EF. So EF and ABC are parallel. And it says give reasons for each stages of your working. Now, again, I'm going to start with this angle here. I've got a chord, I've got a tangent, I've created an angle here. Now, from that chord, I am then so from this chord, we are then creating an angle at the circumference. So we can use the alternate segment theorem and say angle FDB is equal to 70 degrees, and that's because of the alternate segment theorem. Okay, now what can I do next? Well, if we think about this problem, we have a cyclic quadrilateral. So over here, this is my cyclic quadrilateral. So I can work out this whole angle over here because opposite angles in a cyclic quadrilateral add up to 180 degrees. So if this whole angle is 110, 70 plus 40, well, angle EFB, so angle EFB must be equal to 70 degrees as well. And we can say that is because opposite angles in a cyclic quadrilateral add up to 180. So 110 and 70 making 180. So this angle here, the whole angle is going to be 70. And then we can therefore say EFB, so angle EFB is equal to angle FBC because they form what's known unofficially as Z angles, but they are in fact alternate angles. Therefore, if these two angles are alternate angles, then these two lines must be parallel. So we can say these two angles are equal to 70, and that's because alternate angles are equal. So we have alternate angles over here. Therefore, EF and ABC are parallel. And this is how you would do this question. So it's important to be able to even use other angle rules, such as angles on parallel lines as well. Okay. Right. This one over here can be a little bit confusing because you might be in two minds as to whether you use this circle theorem or this one over here. So with this circle theorem, angles in the same segment from a common chord are equal. So if I was to draw my chord here, creating an angle at the circumference over there, and I'm creating another angle at the circumference over here. Therefore, these two angles will be the same. So with this one, is it angle at the center is twice the angle at the circumference, or is it this circle theorem over here? Well, if you think about it, this is our angle. So if this is our chord, we're creating an angle at the center. Now from that same chord, We are creating an angle at the circumference. So this angle is going to be 27 times 2, which is 54. So when it says find the size of angle NOM, we can say it's 54 degrees, and it says give a reason for your answer, and that is going to be the angle at the center is twice the angle at the circumference. And that's nice, 2 easy marks there. But we can apply this to harder problems. So let's have a look at this one. It says work out the size of angle ABC. So we are looking for angle ABC, which is over here. Now, once again, which circle theorem do we use? Now, you might be tempted to label this as 51 degrees. Now, usually the question says the diagram is not drawn to scale, so we can't make any assumptions. But realistically, I mean, these two angles don't look like they are the same size, and we cannot use this circle theorem over here. So angles in the same segment from a common chord are equal because there is no chord here. So this line here is not a chord. It's not splitting the circle into two segments. So this is not, there is no common chord. So the angle that's formed at the circumference here and the angle that's formed at the circumference there, they are not going to be equal. So we cannot use this circle theorem at this moment in time. So which circle theorem can we use? So once again, what is interesting is that if you think about this, and I'm just going to rub this out to make our life easier. So we have a chord over here. So this line splits the circle into two segments. You've got your minor segment here, and then you have your major segment over there. So since we have a chord, from our chord, we have an angle that's formed at the center, which is 64 degrees. From the same chord, we have an angle that's formed at the circumference as well. So this is going to be half of 64, which is 32 degrees. So we can say angle, even though we don't need to explain our answer here, but we can say angle DAB. So DAB is equal to 32 degrees, and your reasoning would be the angle at the center is twice the angle at the circumference. So if the question required you to state that, please do. And then from here, we can work out this angle over here because we have a triangle over here. And it's a little bit frustrating because really the question should label this bit here with another letter, but if it hasn't, it's fine. We can just say this angle is going to be 180 minus 32 minus 51. So 180 minus 32 minus 51 is going to be 97 degrees. And therefore, since this is a straight line and this is a straight line, these two angles are vertically opposite. So this is also going to be 97 degrees. And that's going to help us find the angle ODA. So angle ODA is going to be equal to 180 minus 64 minus plus 97, I should say, in brackets. So 180 minus 64 minus 97 is going to be 19 degrees. So this angle is 19 degrees. Okay, so what is our next step? Well, if we think about this, we have a tangent. So we've got a tangent, we've got a radius. So a radius meets a tangent at 90 degrees. So this angle here, which is angle ADC, is going to be, so angle ADC is going to be 90 minus 19. So ADC is just this little bit here, but we know the two angles add up to 90. So if we do 90 minus 19, that is going to give us our answer, which is going to be 60. Sorry, I should say not 60, but 71 degrees. And that is our answer. So again, two key circle theorems used here. Radius meets a tangent at 90 degrees, and then the angle at the center is twice the angle at the circumference. Right, guys, I hope this has helped. This is, these questions range anywhere between grade 6 to grade 8 level questions. You need to know all your circle theorems. So if you need individual practice on a particular circle theorems, please look at other videos. But this was all about problem solving and being able to apply multiple circle theorems in a problem. All the best and good luck.